Hello, and welcome to Settle the Stars, Episode 19, Exoplanets, A Whole New World. Hey folks, this is Alexander Winn. Last week, we ventured farther away from the solar system than we ever had yet, farther than anything man-made has ever traveled, aside from radio broadcasts at least. We reached the dark and forbidding iciness of empty space beyond the warmth and light of our sun. And today we're traveling even further. If we cut the engines and dim the lights of our imaginary spacecraft, we can fully appreciate the view. The Milky Way sprawls out in front of us, a gleaming metropolis of literally billions of stars. Unaided, our eyes can discern the diversity of them, some bright, some dim, some blue, some red. In the last few decades, we have learned that most of these stars are hosts to their own solar systems of planets, just as the Sun is the host to our solar system. We call these worlds exoplanets, or extrasolar planets, because they exist outside the orbit of our Sun. And as you might imagine, they're incredibly difficult to detect. The huge distance and the fact that most of them don't emit light visible to telescopes have rendered many of these objects undetectable until very recently. But astronomers have developed an impressive set of techniques and technologies to track them down. We've become much better at finding them in recent years, and each new discovery offers more information about how stars and planets form. And with such a large sampling size, astronomers can observe solar systems outside our own in every stage of development, from the newly formed to the old and dying. But the lessons we learn about ourselves and our own solar system aren't the only reason we study the stars. As we know, humans are explorers, and while even the nearest yet identified is an unfathomable 4.24 light-years from Earth, it's only a matter of time before the first interstellar leap, whether it be caused by necessity, desperation, or pure ambition. Extrasolar planets are a natural next step for a civilization founded, enriched, and enlightened by the spirit of exploration. As soon as our solar system began to take shape in our minds, and the model of heliocentrism was accepted and adopted by scientists around the world, we began to wonder about what might lay beyond. Giordano Bruno, an Italian early adopter of the Copernican model, declared in 1584 that, quote, "This space we declare to be infinite. In it are an infinity of worlds of the same kind of our own." While scientists today have certainly withdrawn the expectation of an infinite number of other worlds, Bruno's main idea was spot on. The materials and systematic order present here within our own solar system are present elsewhere in our galaxy and beyond, and where those exist, it stands to reason other stars may develop solar systems of their own. More than 400 years later, the Russian-American astronomer Otto Struve took it a step further. You've heard the name on previous episodes. The Struves were the rock star dynasty of the astronomy world, if ever there was one. In 1952, Otto proposed new techniques for identifying planets outside of our solar system, and in the decades that followed, fellow astronomers began detecting these faraway worlds, adding them to our collective understanding and refining the methods of observation. Now, almost 70 years later, scientists have identified 4,801 potential exoplanets, among 3,552 planetary systems, over half of which have been confirmed. And the pace is accelerating. By the time this episode goes live, I'm sure those numbers will already be obsolete. No one loves naming objects more than astronomers, but even they have to admit there just aren't enough ancient gods and goddesses to go around. We've just about used them all up here in our own solar system. A special, less glamorous naming convention would have to be devised to keep everything orderly, and fortunately the International Astronomical Union, or IAU, is on the case. It was decided that new planets would take the name of their parent star, with a lowercase letter tacked onto the end, beginning with B for the first planet discovered in the system, reserving A for the star itself. So, the planets circling Kepler 89 are named Kepler 89b, Kepler 89c, and so on. Note that they're named in the order of their discovery, not in the order of their orbital distance. It's very possible for planet C to be closer to its star than either B or D. Confusing for future explorers, perhaps, but that's their problem. It's sadly less evocative than a mythological designation, but the naming system does the job for now, and it helps the scientific community communicate about all the discoveries being made. As new planets began piling up, the IAU had to adjust the criteria in 2018 for defining these objects to avoid more confusion. What makes a planet here at home doesn't necessarily apply to the wider universe, so 4 conditions were set. To be considered an exoplanet, an object must first meet the mass requirements for definition as a planet here in our own solar system, and additionally must have a true mass below that at which the fusion of deuterium can occur, and sufficiently low relative mass to the object it is orbiting. Essentially, these conditions exclude brown dwarfs or failed stars, as well as objects near each other in mass like binary systems. With these systems of identifying and communicating about these planets, astronomers have set about categorizing their findings as we build our understanding of how these planets come to be and live out their lives. Superfans of Star Trek can rattle off the classes of planets from Class D, planetoid, to Class Y, toxic, with the nice habitable Class M planets in the middle, but no such system has become broadly adopted by astronomers yet. Several conventions have been proposed to categorize the newly discovered planets by characteristics ranging from composition to size and proximity to their star, but for now, a sort of shorthand descriptor seems to do well enough. We all know what gas giants are, like Jupiter and Saturn. Most of the planets so far fall into that category, so that's easy. Rocky planets are similarly self-explanatory and familiar, as Mercury, Venus, Earth, and Mars would fall into that group. Ice giants like Uranus and Neptune are also found outside the solar system. Less familiar are the kinds of planets we don't have examples of in our own solar system. A hot Jupiter is a term used to describe one such unfamiliar arrangement, where a large gas giant like Jupiter orbits extremely close to its parent star. This contrasts with the cold gas giants that are farther away but lack the icy composition to be considered ice giants. Then you have the warmer counterparts of the ice giants, who spin so close to their stars that their otherwise icy atmospheres have melted entirely, creating worldwide oceans. There isn't as much diversity in the rocky planets, which tend to be on the smaller size relative to the rest of the group, though most are still about 2 or 3 times the size of Earth. The big ones are easier to detect. Some of these rocky planets orbit very close to their stars, and due to the intense heat and gravitational forces never quite cool down. These are known as the lava worlds, and exist in a perpetual molten state, or constantly resurface themselves with massive quakes and volcanoes. Even farther out from their stars, we find rocky planets similar in size to Earth, but many times as distant, which astronomers have called frontier planets. Perhaps even more mysterious are the few rogue planets that have been identified. Entire planets, fully formed, but adrift in open space without a star to call their own. Perhaps formed from collisions of debris or ejected from a host solar system by some cataclysmic collision or a gravitational interaction with another object, these lonesome worlds drift through empty space, dark and frozen. So how do we find all these tiny specks in the void? We've heard on this podcast how difficult it is to find asteroids, moons, and even planets right here in our own solar system. How is it that we can possibly identify them when they're light years away? It's well known that a star is likely to be about 1 billion times brighter than any object that orbits it, a fact that when coupled with the sheer magnitude of distance between us and the system would make the detection of a planet by its reflected light an impossibility with today's technology. In practice, the various techniques rely on the most sensitive instruments for detecting light and other radiation, as well as some elegantly simple optical tricks. When Otto Struve discussed the possibility for exoplanets back in the 50s, he laid the groundwork for one of the most successful techniques used today for finding these planets. It's called the transit method, and it works by steadily observing a star with an extremely sensitive telescope. By comparing the observed brightness of a star, a slight dimming can be spotted as a distant planet moves between its star and the Earth, and by watching the frequency of the transits, the orbital period of the planet can be ascertained. Basically, the planet blocks a portion of the star from Earth's perspective as it orbits, which makes the star's light dim slightly. By measuring the amount of dimming, we can calculate the size of the planet, and by measuring how often the light dims, we can tell how long the planet's year is. One such transit method space telescope was launched into orbit in 2009, called Kepler, after the German astronomer Johann Kepler. The Kepler Space Telescope's sole mission is to discover Earth-sized planets outside of our solar system. and it's equipped with an array of 42 integrated sensors that combine for a total of 94.6 megapixels. Complementing this camera is an extremely advanced mirror, constructed using special glass designed to keep its shape in the wild temperature fluctuations of space, and coated 9 times in silver for enhanced reflection and to detect distortions. Even so technically complex and durable, the mirror is only 14% as heavy as a normal mirror of the same size, an important quality for spaceflight and maneuverability. Unlike the famous Hubble Space Telescope that orbits Earth, Kepler orbits the Sun, separate from Earth, to prevent obstruction and keep a clear view of its target in the sky, a narrow section in the Cygnus constellation. With the help of Kepler's successful cameras, scientists were able to amass a huge collection of new planets. Thousands of new candidates have been identified, many of which could prove to be promising prospects in the search for life. The transit method is by far the most successful technique for identifying exoplanets, but it does have one big drawback. The planets have to be orbiting in a specific direction relative to Earth, so that they pass directly in front of their star. If a star's planets are orbiting at an angle, they'll never pass in front of the star from our perspective, and the transit method is useless. Luckily, there are other ways to find them. Next behind the transit method's commanding lead is a technique called Doppler spectroscopy, sometimes referred to as radial velocity, or more colorfully, as the wobble method. This was another way of finding large planets first proposed by Otto Struve alongside his transit hypothesis, and requires a brief physics lesson to fully appreciate. Light travels through the universe in a perplexing way. Some ways it behaves like discrete particles or photons being sprayed every which way by a star and traveling until they collide with other matter. But in other ways, light behaves like a wave, existing as a series of rays with variable wavelengths. We won't dive too much into that. Physicists have been tearing their hair out over that problem for decades. Suffice it to say for now that depending on the wavelength of the light, humans perceive different colors along the familiar rainbow spectrum from red at lower wavelengths to blue or violet at higher wavelengths. If an object emits waves from all directions equally, those waves will be distributed differently depending on the motion of the object. For example, imagine you're enjoying a nice summer afternoon on a raft in a pool. Your movements send ripples out into the water, but if you're drifting toward one side, the ripples will be bunched up closer ahead of you due to your movement, and will be spaced out farther apart behind you. So in front of you, the ripples hit against the side of the pool quicker, tap, 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 while behind you, they hit the wall of the pool slower, tap, tap, tap. Now you can imagine that a small bug on the side of the pool, with the same deep knowledge of physics and sophisticated measuring instruments that all bugs are known to have, could anticipate your movements in the water without being able to see you at all, just by studying the ripples as they hit the side of the pool. Tap, tap, tap. Uh-oh, the human is approaching. Look out. Or tap, tap, tap. The human is moving away from us. The coast is clear. Essentially, this is what astronomers accomplish with the Doppler spectroscopy method. By studying the light emitted by a star over time, they can detect tiny shifts in the color of the light toward red or blue. These color shifts, called Doppler shifts, are changes in the wavelengths of light caused by tiny movements of the star toward and away from Earth as it wobbles in space. By studying our own sun, scientists are well aware that a large planet can produce such a wobble within a star as it swings through its orbit. Jupiter is massive enough to nudge the sun almost 1.7 times the sun's radius every time it orbits. So by reading these Doppler shifts, astronomers can not only find these large planets, but by timing the wobbles, they can find the orbital period and estimate the distance between the two objects. This method is the second most successful for identifying exoplanets, accounting for almost 900 of the total found so far. Somewhat less successful, but still useful, are direct imaging and gravitational microlensing. Direct imaging is the detection of a planet the old-fashioned way, by seeing it. Fewer than 100 planets have been detected this way, due to the fact that only the largest, brightest planets are capable of sending enough light our way to sense, even by our most advanced telescopes. But gravitational microlensing is a clever trick, limited by the fact that it relies on another rare alignment to succeed. Gravitational microlensing relies on the distortions within space caused by gravity. Any object with mass exerts this distortion, even you. But the larger the mass, the greater the distortion. Much like a bowling ball will cause a mattress to bend down around it, objects bend space around them. This is what causes objects to fall toward each other. They're simply rolling down the incline of the distortion until they collide. But these distortions affect everything that moves through space that has mass, even tiny little light particles. Just like rolling a marble near that bowling ball on the mattress, the smaller ball will get caught in the slope and shoot around behind it. If you aim just right and use enough force, the marble will dodge the bowling ball by banking around the curve on the mattress and shooting on past. For a while, scientists have been studying the same phenomenon in light as it moves around large objects. The photons bank around the curve in space caused by a large object, bent and deflected into a new direction as it passes, almost like a lens bends and deflects light in new directions. By studying these light patterns, an astronomer can determine all kinds of things: the mass of the object causing the distortions, distances, and even the presence of supermassive, otherwise invisible black holes. In 2003, this technique was used for the first time to detect an extrasolar planet. For this experiment, light from a background star was observed as it passed through a different solar system closer to Earth. As the light moved by the nearer star, they compared the distortion and bending to what they expected to see based on the properties of the star it was passing. In addition to the expected gravitational lensing, they detected a smaller distortion caused by a dark object nearby, a planet. You can think of it like rolling that marble on the mattress past the bowling ball, and then seeing its course change again slightly later. Even if you can't see it, you could deduce the weight of the new object by how much it altered the marble's course. This method has been used to detect almost 90 other exoplanets, a tiny number in comparison due to the fact that it relies on the special alignment conditions of a background star as a light source. The final method accounts for the smallest number of exoplanets, but it's very useful for detecting smaller, rocky planets, particularly interesting for future stellar explorers hoping to find a planet like Earth. This method is called transit timing variation, and it works especially well for systems with multiple planets in compact orbits. This technique relies on the other detection methods and the gravitational interplay between objects as they orbit their star. As planets move around the star, they tug at each other, causing their orbits to speed up or slow down very slightly. If an extrasolar planet within the system has already been detected by scientists using the transit method, they can then observe that transit over time to exactly measure the period of the orbit. If that orbit then changes in any way over time, those changes can be used to calculate the mass or masses of other objects in the system that could be causing the change. Sort of like estimating traffic based on how late your students are to class, you can detect new exoplanets based on the fluctuations in the orbits of other exoplanets you already know about. So, with all of these techniques, scientists have significantly expanded the catalog of known planets. We've seen how their size and distance to their star can be detected, but these qualities also have a lot to do with another important aspect of space exploration: habitability. After all, if you're going to invest the time and energy to travel trillions or quadrillions of miles, you'll want to be sure where you're heading has a pretty good chance of being somewhere you want to live. For humans, that means water. Aside from beautiful waterfront property, liquid water is absolutely essential for life as we know it. It insulates us from the wild variations of heat and cold common in space. It provides an environment for soluble molecules to interact and react with each other, and it plays an important role in many metabolic processes. Whether we're looking for existing life or scouting a spot to call home ourselves, wherever it is, it'll need water. Astronomers have worked out how to calculate the range from any given star that should allow for liquid water to exist. These Goldilocks zones vary from each star due to the heat and size of the star in question, but can be determined with a fair degree of certainty once the relevant details from the star are known. So far, of the approximately 3,000 confirmed exoplanets, several hundred have been determined to orbit within their star's habitable zone. Extrapolating this sample size to the galaxy as a whole, scientists estimate that as many as 300 million planets could exist within habitable zones in the Milky Way alone. As of right now, several potentially Earth-like planets have risen to the attention of astronomers and interplanetary daydreamers alike, but one recent discovery stands out. In 2020, data from the Kepler Space Telescope revealed Kepler 1649c. While 300 light-years away may seem impossibly distant, it's just around the corner in galactic terms, less than 1/3 of 1% of the Milky Way's diameter. This rocky world is about the same size as Earth, and was discovered using the transit method. But before you suit up, you should know that the planet closely orbits a dim red dwarf, completing an entire orbit once every 19.5 Earth days. Not that you'd have any chance of seeing it yourself if you headed out in a spaceship using current technology. At that rate, your journey would take over 11 million years. Probably wise to wait for warp travel to be invented. That being said, the whole idea of a Goldilocks zone itself may be a flawed one. It's easy for us as humans to confuse the idea of habitable for us with habitable for anyone. In the search for extraterrestrial life, it's generally accepted that liquid water is required, but that does not mean the planet has to look like Earth. We've already seen that liquid water exists all over our own solar system, well outside the traditional definition of our sun's Goldilocks zone, for example under the ice of Europa and even more distant worlds. Atmospheric pressure also plays an important role. On Venus, with its atmosphere of more than 90 times as thick as Earth's, water won't boil until you reach 560 degrees Fahrenheit, or almost 300 degrees Celsius. That means you could have a planet that is more than twice as hot as boiling water on Earth, and still have oceans teeming with alien life, if the atmospheric pressure is high enough. If we're looking for planets habitable to humans, the Goldilocks zone is quite narrow. But if you expand the definition to simply mean anywhere you can find liquid water, it opens up tons of new potential candidate worlds. But what are some of the other notable mentions among the exoplanets? Surely there are some strange worlds we've discovered waiting out there. A word of warning as we dive into a few of these. As we discussed earlier, the names for some of these stars can be a little unglamorous. Take PSR B1620-26b, for example, the first planet discovered that exists in a circumbinary orbit. That means it orbits a pair of stars, not just one. HD 20781b and HD 20781c have one-upped the complexity in their system even further. These planets orbit a star in a binary system as well, but the other star has planets of its own too. PSR B1257+12b is known as a super-Earth, still quite smaller than a gas giant, but much larger than Earth. Some of these gigantic rocky worlds can be as large as 15 or 16 times the size of Earth. By the way, the star known as PSR B1257+12 is also known as Lich, after the undead monster of fantasy and folklore, and that is just unspeakably awesome. Sometimes a planet can form too close to the sun to last long against the torrent of heat and light. KIC 12557548b is one such planet, small and rocky, yet trailing a giant cloud of dust like a massive comet as it is slowly burned away by its own star. And then there's one of the rogue planets, OGLE 2016BLG1928. This Earth-mass planet was detected with gravitational microlensing in 2020 and wanders free in the darkness, unaccompanied by any star. There are many more exciting exoplanets to explore, but my mouth is getting tired of the names. As scientists collect even more data on the newly discovered planets, other mysterious or strange worlds will continue to pique our curiosity and kindle our imaginations. I hope you've enjoyed our time today learning about the search for exoplanets and some of the exciting possibilities they represent. Future explorers will certainly have their work cut out for them when the time comes to launch, but in the meantime, astronomers and the intrepid crew behind the Kepler mission will continue to add more exoplanet discoveries, just as fast as they can come up with incomprehensible strings of gibberish to name them. Please tune in again next time as we continue our journey through the universe by turning back and making our way home. In the meantime, be sure to subscribe if you haven't already. Settle the Stars is available on pretty much every podcasting platform, and we're also mirroring our episodes on YouTube at youtube.com/edgeworksentertainment. And be sure to ring that bell so you know when there's a new episode. We also have a Patreon page at patreon.com/edgeworksentertainment, where you can get early episodes and tons of other great rewards. The support of listeners like you is what makes this show possible, and I'm so grateful to the people who have already joined. And if you haven't already, please leave a review for the podcast on whatever platform you use to listen. It really does matter for indie podcasters like me. Thank you all for listening, and as always, happy terraforming. Settle the Stars is a proud member of the Edgeworks Nebula, a collection of intriguing and informative podcasts from Edgeworks Entertainment.
Edgeworks Nebula.